This is the video lecture over the fourth section of the chapter entitled Fundamentals of Probability. You'll notice that this section is a pretty big detour from what we were talking about before with counting methods, but those counting techniques and probability will get linked together in the next section. So we're going to bring it all together in the next video. First we have to get this idea of probability down. So you probably already have a pretty good understanding of what a probability measures. Probability measures how sure you can be that something's going to happen. Probabilities are numbers which describe how likely it is that a particular event will occur. And the bigger the probability is, the more likely it is that the event will occur. If the probability is small, that means that it's a fairly rare event. If the probability is large, it means it's a fairly common event. Those are intuitions that you probably already have about probability. We're just going to formalize all of this to make sure that there aren't any gaps. We need to start with our process, which we call a probability experiment. A probability experiment is a procedure where the outcomes are determined by chance. So there's some sort of randomness involved in the outcomes of the experiment, of the procedure. That's what makes it a probability experiment. The two most basic types of probability experiments are where you're flipping coins, assuming that you're not doing any kind of manipulation to make a particular side come up because you're some kind of magician or cheater, and rolling dice. Again, assuming that you're not in some way manipulating the die to get a particular number or anything like that. These are prime examples of probability experiments, but probability experiments can be much more general than this. You could talk about randomly selecting 15 people, asking them their opinions on a particular topic. Or you might randomly select 50 cats and determine the number of hours that they sleep each day, right? Those outcomes are determined by chance because you're randomly selecting the individuals, whether they be people or cats, for the experiment. Those are probability experiments. We're going to focus on these basic kinds here because we're going to be able to come up with what's called their sample space, and that's our next definition. The set of all possible outcomes of a probability experiment is called the sample space of the experiment. Sample space is just a fancy way of saying that you're listing everything that can happen in the experiment. Because it's a set, we're going to use a capital letter for its notation, and the most common notation is a capital S. So the sample space of a probability experiment is often denoted by S, and here we're going to actually look at a couple of sample spaces because the concept sounds complicated, but it's actually not too bad. Our first experiment is to flip one coin. Now on each side of a coin, there are sides that we usually refer to as heads and tails. On American money, almost every American coin has some person's head on the front, but the side with the head on it we call heads, and then that other side we call tails. And so the sample space for this experiment is the set, remember that it's a set, containing those two outcomes, heads and tails. And since that's the list of everything that can happen, right, we're not going to do some weird thing where you flip it and it lands on its side. To take that smart alecky response out, imagine you're catching it, flipping it, and smacking it on your hand. That's the list of everything that can happen, so that's our sample space. Because we'll be talking about coins quite a bit, both in lecture and in the book, you might want to think of the abbreviations H and T as a more concise way of writing heads and tails. So that's a list of everything that can happen in the experiment. We call that the sample space for this experiment. The other common probability experiment is rolling dice. So here we've got the experiment where we roll one die. Die is the singular of dice. And I put a picture of the 6 faces that can be on the top of a 6-sided die. And when we talk about dice in class, unless we say otherwise, I want you to assume that it's a normal cubic 6-sided die, not one of those 100-sided golf ball size Dungeons and Dragons dice or anything like that. Just standard board game 6-sided dice. The sample space is the set containing those outcomes. And rather than drawing the pictures, I'm just going to write the number of pips, that's what you call each of these dots, they're called pips, on the top face. So you could get 1 or 2 or 3 or 4 or 5 or 6 pips on the top. And that's the list of all the possible outcomes, so that's a sample space. For probability purposes, we'll want a sample space where each outcome is equally likely, where they all have the same chance. But we'll get into that in a second. One more definition before we can formally define probability, and that's the idea of an event. Using our nerdy language from the set theory chapter, an event is simply a subset of the sample space. So an event is a collection of possible outcomes from the sample space or an empty set. So an event just describes one scenario of the experiment. And it could even describe an impossible event. That's where the empty set will come in. Just like a sample space, an event is a set. It's a subset of the sample space. And so we use a capital letter for this as well. Your author uses E almost every time, but if you're doing an example where you've got multiple events described for the same experiment, you might use other letters, like it would be common to use capital A, capital B, capital C, etc. Your author typically uses E. You'll notice that in our definition for probability. Technically, this is what we call theoretical probability. I don't like to call it that because students get the wrong perception from that name. So we're just going to call it probability. If an event E has n of E equally likely outcomes, so E has n of E elements in it, and its sample space has n of S equally likely outcomes, n of S would be the number of elements in S, then the probability of an event E, denoted by P of E, is P of E equals n of E divided by n of S. This, again, seems complicated, but the concept is actually pretty straightforward. Let me go back to that example where we were flipping a coin, and we'll talk about a probability that I bet you already are familiar with. Suppose you've got a coin that's machined in such a way that it's a fair coin. That is, when you flip it, heads and tails are equally likely. And I want you to tell me, what is the probability that the coin comes up heads? I bet you don't need a fancy formula for that. You probably have an intuition for it. You're probably thinking that it's 50% or 1/2. And I'm going to write the answer as 1/2 using our rule. Go back to the nerdy rule. The nerdy rule says if the event has n of E equally likely outcomes, then that's the numerator of your probability. So going back to this, how many outcomes in the sample space are heads? Well, just one. There are only two sides and only one side has heads. The denominator of your probability is the total number of elements in the sample space. The sample space S has n of S equally likely outcomes. That's the denominator. Going back, there are two outcomes, and so the probability is 1/2, just like you already knew. This follows your intuition. Where this is useful is where there are more than two outcomes. This isn't a very difficult example, but when the probabilities get more complicated because there are more possibilities, this definition comes into play. You'll notice that it requires that each of the outcomes in the sample space be equally likely. Everything has to have the same chance. A common misconception that people have about probability is that events have a 50-50 likelihood of occurring because either it's going to happen or not. People use that to justify things all the time. They'll say, well, I'm going to play the lottery because I'm either going to win or I'm not, so it's a 50-50 chance. That's not what probability means. Probability doesn't tell you how many possibilities there are. Probability tells you how likely something is to occur, what fraction of the time you can expect it to occur. If you expect to win the lottery 50% of the time, you're fooling yourself. So that kind of thing doesn't work. If you're taking a half-court shot in basketball behind your head, you're either going to make it or you're going to miss it. There are two things that can happen, but they're not equally likely, so you can't say that the probability of making it or missing it is 1/2. We can do that in the coin example because we're assuming that the two sides are equally likely to come up. But if the two events are not equally likely, you can't use that rule. So please don't misuse probability that way. It drives me crazy. Let's look at some examples from the text. Page 309. There's a selection of problems. We're going to do a few of them. It says, a die is rolled. The set of equally likely outcomes is the set containing 1, 2, 3, 4, 5, 6. When they say the set of equally likely outcomes is this set, that's just a fancy way of saying that this is the sample space. And so this is the set S. for our definition. Then they ask us to find a bunch of probabilities. Number 2 asks us to find the probability of rolling a 5. So if you're familiar with dice, you probably already know what this answer is. Let me first talk about notation. You'll notice that the notation that we use is P of E. So you can write the capital letter P and then the event to mean the probability of rolling a 5. In the definition, let's start with the denominator. The denominator is the total number of outcomes in the sample space. That's 6. The numerator is the total number of ways that your event can occur. Well, how many different 5s are there in the sample space? Just one. There's only one way to roll a 5, and that's to get the picture with 5 pips on the top. So the probability of rolling a 5 is 1/6. So what exactly does this answer mean? It's basically a long-term expectation. It tells you that if you were to roll this die many, many times, the fraction of the time that it would come up with a 5 is 1 out of every 6 rolls. That's one way to interpret this. There are a lot of people who would prefer to think of probabilities as a percentage of the time that something happens. So the percentage equivalent to 1/6 is close to 16.7%. That's not exact, but it's close. It means that about 16.7% of the time that you roll a 6-sided die, you'll roll a 5. It won't be exactly 16.7%, but it'll be close. In the long run, it should get closer and closer to 16.7%. A good rule of thumb is to say that an event is uncommon or rare if it happens less than 5% of the time. This happens way more than 5% of the time, so it's not uncommon, but it's not overly likely either. You're much more likely to not roll a 5 than you are to roll a 5. Problem number 6. Find the probability of rolling a number greater than 4. So the probability of rolling a number greater than 4 let's see. The denominator will be 6 because there are 6 outcomes in the sample space, right? That's what our rule says. The denominator is the number of elements in the sample space. The numerator will be the number of elements in the sample space that satisfy this condition. How many numbers in the sample space are greater than 4? Well, there are 2. That's 2/6. And I know that reduces to 1/3, and quite honestly, I'm getting the shakes not reducing that. I really want to. But I want to show you that I don't care if you reduce your fraction, so you can just leave it as 2/6. For those of you that prefer percentages, this is about 33.3%, not exactly, but close. So around 33% of the time that you roll a 6-sided die, you'll roll a number greater than 4 in the long run. If you just roll a die 3 times and count how many times you get a number greater than 4, it might not come up exactly 1/3 of the time. It could be less, it could be more. But if you were to roll a die 3 million times, the number of times that you rolled a number greater than 4 would be really close to 1/3 of that, so 1,000,000 of them. Same example, but 2 more special cases. Die is rolled, we've got our 6 outcomes. Problem number 7 asks us to find the probability that the number we get is less than 20. I'm going to stop writing the probability statements and just write the answer off to the side here. So the denominator will be 6. There are 6 outcomes in the sample space. The numerator will be the number of outcomes in the sample space that are less than 20. Well, they're all less than 20. There are 6 outcomes in the sample space that are less than 20. And where I said I didn't care if you reduced before, here I am going to reduce this to a 1. You are welcome to leave this as 6/6. But I want to show you that that answer comes out to 1. This is the largest possible probability. It corresponds to 100%. And if an event has a probability of 100%, it means that it's guaranteed to happen. We have a nerdy name for it. We call it a certain event because it is certain to occur in the experiment. But you can just think of it as being for sure. It's definitely going to happen. This is the largest possible probability. Probabilities are never bigger than 1. You can't have a probability of 120%. I know there are sports cliches where you can give 120%, and I know that you can have a 120% increase. I'm not saying that percentages can't be more than 100%, but probabilities can. The maximum probability is 100%, or 1 in decimal form. Problem number 10 is the other special case. Find the probability that the number you roll is greater than 8. So the denominator will be 6. The numerator will be the number of values in the sample space that are greater than 8. Well, none of them are greater than 8. The maximum number you can roll on a typical 6-sided die is 6. So there are no outcomes in the sample space that satisfy that definition. And again, you could leave your answer like this, but I'm going to reduce that to 0. 0 divided by 6 is 0, and as a percentage, that's 0%, which means that this event occurs 0% of the time. And we have a much more common name for this. This is a word I'm sure you've used before. We call such an event impossible. This is an impossible event. Any event that has probability 0 is impossible. It cannot happen. So these two examples demonstrate the extreme special cases. An event that must occur has probability 1 or 100%, and an event that cannot occur in the experiment has probability 0 or 0%. Let's look at some slightly more complicated experiments. I'm skipping over the card examples because I know some of you aren't familiar with cards, but if you're into playing card games, I encourage you to do those card examples because they're fun to do. I used to play a lot of online poker when it was semi-legal. I won almost $1,000 playing for nickels and dimes. I'm a wuss, so I didn't play for a lot of money, but I played a lot and I wound up winning almost $1,000, which I immediately had to spend on my wife, but so it goes. That's what happens when you marry somebody who's way prettier than you and way smarter than you. You do anything you can to hang on to them. Anyway, I'll give you more terrible life lessons later. Let's get back to the math. On pages 309 and 310, there's this experiment where we flip a coin twice. Notice that they specify that the coin is fair, so that the sample space can be used for probability purposes. It says a fair coin is tossed 2 times in succession. The set of equally likely outcomes is, and then they give us this notation, and I want to remind you that we use H for head and T for tail. So the way to read this is that one outcome is that you get heads on the first flip and then heads on the second flip. Or you could get heads on the first flip and tails on the second flip. You could get tails on the first flip and heads on the second flip, or you could get tails both times, for a total of 4 outcomes. We know from the counting section that there must have been 4 outcomes because the first flip can come up 2 different ways, and the second flip can come up 2 different ways, and 2 times 2 is 4 by the fundamental counting principle. So we know the sample space has to have 4 outcomes. But this sample space is small enough that we can just list them. So this is our sample space S. Then he asks for some probabilities. Again, I'm not going to write out the probability notation every time, but maybe in this first example where I've got some space, I'll do that. The first one says, find the probability of getting 2 tails. So the way we would denote that is P, and then we would describe the event, 2 tails. Recall our definition. The denominator is the number of equally likely outcomes in the sample space. There are 1, 2, 3, 4 outcomes, or remember we counted that up by fundamental counting, so the denominator is 4 before we reduce. The numerator is the number of outcomes in the sample space that have exactly 2 tails. Well, this doesn't have any. This only has 1. This one has 1. There's only one way to get 2 tails. That's when you get tails on the first flip and tails on the second flip. And so that comes out to 1/4. As a percentage, that's 25%. So a quarter of the time that you flip a coin twice in a row, you'll get 2 tails. You'll get tails both times. And again, that's a long-term expectation. If you take a coin out right now and flip it twice, and then do that 4 times, you might get 2 tails twice, or you might not get 2 tails at all. But over the long run, if you were to keep doing this, about 25% of the time, there were 2 tails. That's what that answer means. Number 24 says, find the probability of different outcomes on each toss. Don't worry about writing the notation, but I want you to try to do this one. Come up with the numerator and denominator. Go back to the definition if you need to. Let's see if you got it right. I'm not going to write the notation because there's not enough space. The denominator will be 4 because there are 4 outcomes in the sample space. As long as you haven't changed the experiment, the denominator is going to be the same every single time before you reduce. It might reduce to something else. But as you start, the denominator will always just be the total number of elements in the sample space. The numerator is the number of ways that you can get different outcomes on each toss. Well, these are the same, so I don't want to count that one. Heads and tails, that's different. Tails and heads, that's different. Tails and tails, that's the same. So these two have different outcomes. That's 2 out of 4. And again, it's going to drive me nuts not to reduce that, but I'm not going to. You guys know that that reduces to 1/2. That's 50%. There's a 50% likelihood that you'll get different outcomes on each toss. One more example from this experiment. Number 26 asks us to find the probability of getting at least one head in your 2 flips of the coin. So we'll walk through this together. The denominator is going to be 4. Until we change the experiment, it's going to stay with 1, 2, 3, 4 outcomes. At least one head means one or more. We've talked about what at least means earlier on in the course, but I just want to remind you. At least one is a greater than or equal to statement. So at least one head means one or more. This has 2 heads, that's at least 1. This has 1 head, that's at least 1. This has 1 head, that's at least 1. This has 0 heads, that's not at least 1. There are 3 out of the 4. That's 75%. If you think about it for a minute, we could have guessed that this was 75% based on our answer to number 22. If the probability of getting 2 tails, or no heads, is 25%, then the probability of getting at least 1 head, which is the opposite or complement of that, would be 75% because the total has to be 100%. That's a rule of probability, that the probability of the complementary event can be found by just subtracting from 100%. We didn't need to use that here because we have the sample space, but you certainly could have done it that way. If you thought of it that way, that's good. That's a slick way to go about this problem. Let's look at a more complicated sample space. Not a more complicated experiment. We're just going to roll a single die twice. And so off in the corner here, I've got the sample space of 36 possible outcomes. How did I know that there were going to be 36? Fundamental counting tells me that. There are 6 ways the first roll can come up, and there are 6 ways the second roll can come up. And 6 times 6 is 36. So there are 36 outcomes in the sample space. And if you look, this picture has 6 rows and 6 columns, so there are 36 pairs of dice there, 36 outcomes in the sample space. Then he asks some probability questions, like the first one says, find the probability of getting 2 odd numbers. Now, there are advanced ways to come up with this, but we're going to do this with the sample space first. What is the probability of 2 odd numbers? I have enough room for it here. So I want all of the outcomes where both numbers are odd. So we could just go through and count. There's the 1 and the 1, the 1 and the 3, the 1 and the 5. I can skip all of the second column because they all have 2's. 3 and a 1, a 3 and a 3, 3 and a 5. The fourth column all has 4's. A 5 and a 1, a 5 and a 3, a 5 and a 5. These all have 6's. And so for both numbers to be odd, there are 9 possibilities. And what will the denominator be? Well, remember, we've already counted there are 36 total outcomes. So that's 936, which reduces to 1/4, or 25%. I keep writing the percentage off to the side in case you find that as an easier way to interpret probability. You don't need to do that for me. The fractional answer, reduced or unreduced, is perfectly acceptable. So 936 can be your final answer. Just for people who like to think in terms of probability, as a percentage, I'm going to keep writing the percentage, if I can do it. I can't help myself. There's a slicker way to find this probability, and this leads into what we're going to talk about in the next section. This brings us back to our counting techniques. So the denominator we could get by 6 times 6. Let me do this in another color. So here's a slicker way to do this. The denominator would be 6 times 6 using our counting technique. 6 ways the first roll can come up, 6 ways the second roll can come up. The numerator, we could take the number of odds on the first roll times the number of odds on the second roll. There are 3 odd numbers on the dice, so there are 3 ways we can get an odd number on the first roll, and there are 3 ways we can get an odd number on the second roll, and sure enough, this comes out to 936. You can't always use this trick. In fact, the very next example, you can't do that. But it's a nice way to do it, especially when the sample space starts getting really, really large. Like here, we're only rolling 2 dice. There are 36 outcomes. If you roll a die 5 times, there are 7,776 elements in the sample space. And then writing them all out and trying to weed through isn't a very practical way to do it, so we use tricks like this. Here we could just count. I want you to try to do number 38, which asks us to find the probability of rolling 2 numbers whose sum is 6. Remember that sum means that they add to 6. Pause the video and see if you can come up with that. Okay, let's see if you got it right. The denominator is going to be 36. The numerator is going to be the number of pairs of dice in there whose sum is 6. And it might take you a little while to find them, but if you notice, they all fall on this diagonal. All the diagonals add up to the same number. So right here, those outcomes all add up to 6. So there are 1, 2, 3, 4, 5 different outcomes that sum to 6. 536 doesn't reduce, and I think that's pretty close to 14%. I think it's just under 14%. So you're playing some board game with your little niece or nephew, and of course you want to crush them, and you need to roll a 6 to beat them. You've got a 14% chance of ruining their hopes and dreams. Number 39, last one. Find the probability of getting two numbers whose sum exceeds 12. Pause the video and see if you can come up with that. If you're familiar with dice, you probably know what the answer is already. If you're not familiar with dice, let's walk through it. There are 36 total outcomes in the sample space. And how many have a sum that exceeds 12? Well, these are all too small. That's only 8. The biggest outcome is 12. There are no outcomes whose sum exceeds 12. The best you can do is 12. We call that boxcars, or at least they did a long time ago. I don't know, I'm old compared to you guys. So there aren't any outcomes in the sample space whose sum is greater than 12. As a fraction, that's 0 over 36. You can write that as just 0. I would accept either of those answers. And of course, that's 0%. You can't roll a sum that's bigger than 12. So you're still trying to destroy this little kid that you're playing the game against. And in order to beat them, you're going to have to roll a sum bigger than 12. Well, you better cheat, because you can't beat them. It's impossible for you to roll a number bigger than 12. So it's time to do them dirty and just show them how the real world is. Okay, those are the basic examples, and most of the problems in the section are these kinds of examples. There's another example where you're talking about children being born into a family, but it gives you the sample space. There's one with a picture with a spinner, and again, if you're into cards, I encourage that you do the card problem, but that will not be on the exam. If you have any questions, let me know.